talk more. So next talk is also SOS, degree 4 SOS lower bound for the clique number of the Paley graph, and Tim will give the talk.
Okay, so am I supposed to be wearing something? Can I just, should I just project or? Okay. Hello? Oh. Okay. Right, so thanks for the opportunity to present here. So I'm not a complexity theorist at all. Don't know why I'm here, but I'll try to convince you that these things that I worked on with Shifan Yu, a great student in our department, might be of interest to this community. So we've seen in several of the talks this kind of theme of trying to prove lower bounds in proof complexity by finding some propositions that we expect to be hard for various proof systems. So here are some examples of things that we've seen or that have been mentioned. So these Taden tautologies, which are some kind of parity systems or contradictions, parity systems on graphs. Pigeonhole principle can be kind of encoded as a proposition you can ask proof systems to prove. Just from the last talk, and I think this was mentioned yesterday, the existence or non-existence of small circuits given a truth table, this kind of more algebraic matrix inverse property, and there are lots of other propositions that have kind of come up in this literature. You all probably know better than I do, but there are lots of these kind of combinatorial problems that are used for this. There's a whole big class of random problems, like random, let's say SAT, random constraint satisfaction problems of various kinds. I want to bring your attention to one interesting example that I'll try to kind of draw a parallel between what I talk about and this, which is there are some results about the statement of Ramsey's theorem. So given a graph, there exists a coloring, right, et cetera, or sorry, for any coloring of a graph, or let's say the complete graph, there exists a clique or independent set of some size. And this has been shown to be a hard statement when written down as a proposition to prove for various proof systems. And this, I claim, is kind of different from the rest of these in that this is really a sort of non-trivial piece of mathematics, right, that can be kind of leveraged into a proposition that's hard for proof systems. And so I'll try to convince you that this maybe kind of what's going to seem like a rather unusual topic is actually kind of in the same sort of vein. So the title refers to the Paley graph, which is this object from number theory. So let me tell you about this. So to build the Paley graph, we take a finite field of prime order, so Z mod P. P will have to be 1 mod 4 for a reason I'll mention in a second. And we're going to build a graph whose vertices are the numbers mod P, right? And to decide whether two of them are connected, we subtract them mod P, and we check whether that is a square or not, mod P. So some numbers are equal to another number squared, mod P, and some are not. So for example, you can try to square all the numbers mod 5. You'll find that the squares are 1 and 4. Right? 4 is the same as minus 1. So if you connect every number mod P, every pair of numbers whose difference is either 1 or minus 1, you just go in one direction or the other around the cycle. Right? So the Paley graph of size 5 is the 5 cycle. So how do we expect this graph to behave? There's this heuristic from kind of analytic number theory that the operations of addition and multiplication behave as though they are sort of statistically independent. So in particular, sorry, not just yet. So we're kind of using addition when we subtract two numbers mod P. Right? And we're using multiplication when we check whether that difference is a square mod P or not. So if we believe this heuristic, we should believe that adjacencies in the Paley graph between pairs of vertices should look kind of statistically independent. And so there's this high-level heuristic that the graph should look sort of pseudo-random in some sense. And so to understand kind of what random graph it should look like, we should kind of calibrate some basic quantities. In particular, you can check that half the numbers are squares or non-squares mod P, right? And so maybe based on that, we should believe that the Paley graph should look like an Erdős-Rényi graph on P vertices with edge probability 1/2, right? That would give us the same expected typical degree. Okay. So you can find lots of kind of simple examples of this heuristic holding. For example, if you count, let's say, triangles or any finite subgraph in the Paley graph asymptotically as p goes to infinity, you'll get the same value as you would in expectation over an Erdős-Rényi graph. So this expectation of the number of triangles in an Erdős-Rényi graph is some simple kind of combinatorial linearity of expectation calculation. The number of triangles in the Paley graph is complicated. There's some kind of character sum stuff you have to do, which I'll talk about a little bit later, but you get the same asymptotics to leading order. Okay? Interrupt me if you have questions. So you can ask, okay, how far can we push this heuristic? In particular, instead of just looking at these small kind of finite motifs, right, you can ask about more extremal questions about what kinds of large subgraphs of size, depending on p, exist or don't exist in the Paley graph. So a kind of typical example of this kind of question is asking for the clique number. What is a clique? Is a complete subgraph, right? What is the size of the largest clique in this graph? So again, we expect this to probably behave something like an Erdős-Rényi graph. For an Erdős-Rényi graph, it's kind of a not too difficult probability exercise to calculate that the typical size of the largest clique is of order log p, log the number of vertices. So it turns out that the same thing definitely does not quite hold for the Paley graph. So there are some results from number theory literature that say that at least for an infinite sequence of primes, I forgot to mention, so p has to be 1 mod 4 so that the difference, the adjacency relation is symmetric between, I just realized. So that way, j will be adjacent to I if and only if I is adjacent to j, because x will be a square if and only if negative x is a square. Anyway, doesn't matter. So you can show that there's an infinite sequence of primes so that are 1 mod 4, so that this exceeds log p by this log factor. What does a drowning number theorist say, right? And there are some numerical experiments I'll show you in a second that suggest that maybe the true scaling should be like log p squared. But in any case, we definitely believe the true value to be kind of polylog of p. On the other hand, the best upper bounds that we have on this are all of order square root p. For a long time, and there are lots of different proofs of this, the best known upper bound was truly just square root p. And then a few years ago, this was improved. This was kind of a breakthrough on this subject, but just improved in the constant factor in front of square root p, and this is the best bound known right now. Okay. So here's a plot of the real clique numbers fit kind of in an ad hoc way to log p squared. Does it look convincing? Not convincing. I don't know. Sort of. But definitely, right, looks like some bigger scaling of this would be a plausible upper bound. It's hard to resolve these kind of very slow asymptotics, right? This is p going up to some 15,000, 17,000, but you need to take very, very large p, and it's hard to calculate the clique number exactly. Anyway, so this has been an open problem in number theory for a long time, and there's this, this has to do with other kind of classical number theory questions. But there seems to be this kind of barrier at this square root p scaling past which we don't know how to improve upper bounds on the clique number of the Paley graph. Okay, so what does this have to do with this conference? So, maybe if we have this kind of hard problem, we can build out of it a proposition, which is that the clique number is small. That we might expect to be hard for some restricted proof systems that are sort of amenable to, writing down this kind of more quantitative statement than the sort of combinatorial constraint satisfaction types of things that we've seen before. And so again, I claim that this is kind of analogous to this Ramsey's theorem situation. So this is not even known to be true, but it's kind of believed to be true. But if it is true, it's probably a difficult theorem. You could try to encode like that this is at most, root p over 2. That's something that we know to be true. And these are really kind of non-trivial facts, and we can try to still argue that they're hard for restricted proof systems. Okay, so let me talk about the proof system that I'll work with, which is going to be similar but not quite the same as the previous talk. So for the purposes of computing the clique number, we can start with this sort of polynomial formulation of this as an optimization problem. So here, right, these yi variables are the indicators of membership in a clique. Right? We're trying to find the size of the largest clique, so we're maximizing the sum of the indicators, which is the size of the clique. Right? This yi squared equals yi is a polynomial way of writing down the constraint that they're either 0 or 1. And so we want, if two vertices are in the clique, then they have to be adjacent. So in other words, if two vertices are not adjacent, then one of them has to not be in the clique, and this yj equals 0 is writing down that constraint. So this is a polynomial optimization problem that is just equal to the clique number. So given any such kind of situation, we can ask for sum of squares proofs of bounds on this. So in the previous talk, we saw some discussion of sum of squares refutations of statements, so proofs that some kind of equality, some system of polynomial equalities, let's say, can't hold. Here, I'm asking for a proof of an upper bound on my objective function. So if I have some number c and its difference with the objective function is this same kind of expression that we saw before on the right, which is greater than or equal to 0 on my entire feasible set, then this is a proof, a sum of squares proof, that the objective function on the feasible set is at most c. And algorithmically, the nice thing about sum of squares is that if we constrain the degrees, all of the polynomials appearing here, then this is kind of, I think, automatizable is the term, right? You can write this, you can write an algorithm that optimizes the bound c, right, using semi-definite programming. And in an amount of time and a size of semi-definite program, that kind of scales up with your degree bound. So I'll note that people have talked about polynomial calculus and stuff here, and there's a distinction between this type of proof system and that, which is that here we're talking about just kind of a static proof. So you have to kind of give the entire proof in just one sentence, one object, and we're measuring the size of that thing. Right? So there are no axioms and kind of derivation rules. It's not one of these dynamic proof systems. There's a sum of squares version of that, but that's not what I'm talking about. Okay, so now what's maybe one step less familiar is that because of this connection with semi-definite programming, there's a dual formulation of these semi-definite programs coming from sum of squares, which it turns out will be sort of useful for proving lower bounds. So let me go over how this works. Imagine let's just forget about all of this sum of squares proof stuff, and we'll derive another way to write down semi-definite programs that give bounds on the clique number. So here's the recipe. I'll take my variables y that I'm trying to work with, and I'll stack monomials in y into a big vector. And I will write down the rank 1 matrix x built from that vector of monomials in y. Right? Now, if I could optimize over all of these rank 1 matrices, because I'm including 1 as a monomial, right, x contains, somewhere in its entries, and let's say the top row, it contains y1 through yn, right? So if I could optimize over this set of x's, I could just optimize directly over my feasible set, and I could just solve the problem. But I can't. The set of these x's formed like this is kind of very complicated. And so I'm going to write down some subset of constraints that this x has to satisfy and try to optimize over that. So here are the constraints that we'll use. So the really kind of intractable thing is that x is rank 1. It's hard to impose this, let's say, in a semi-definite program. But we'll remember, we'll forget that x was rank 1, but we'll remember that x was positive semi-definite. Okay? Then we'll try to find some kind of consequences of these other green and orange constraints. So the kind of Booleanness constraints, the yi squared equals yi, will imply that if I have, is there chalk here? So if I look at the entries of x, I have xij, this is going to be y to the I times y to the j, right, in this rank 1 matrix kind of setup. So if there are any entries repeated in these, so this is really like yi1 and yj1. So if there are any entries repeated in I and j, I can use this Booleanness constraint to kind of remove those repetitions. And so this will only depend on the set of indices cumulatively occurring in I or j any number of times. Also, so there's this normalization. I'm including the kind of empty monomial, right? So that should equal 1, just because, I don't know, kind of anything to the 0 is 1. And these edge constraints imply that x at any set of indices should be 0 whenever that set does not form a clique. Right? Okay, and now I'll just look for where does my objective function kind of happen in x, and I'll optimize over that. And so this is going to be another semi-definite program, right? Because I have one PSD constraints and a bunch of linear constraints. And it turns out that this is exactly the convex dual of the semi-definite program encoding the thing from the previous slide. And the reason this is nice is that this semi-definite program is a maximization. So if we want to prove lower bounds, we just have to build a feasible point for this thing, so-called dual certificate, if you want. So here's an example. Maybe I won't spend too much time on this, but so this is for the very first one of these where this little d, degree bound equals 1. So here you see in green I'm kind of using, so like let's say x of 1 in green there should be x of the set 1 union the set 1 or something, but I'm kind of applying the constraints. A matrix like this, so indexed by the empty set, and the singletons has to be PSD. Right? And the clique constraint, well, the sizes of set appearing here all have size at most 2, so the only kind of non-cliques that can happen are just the non-edges, and so this matrix will have to be 0 on the non-edges. So this SDP is the same as the Lovász theta function for bounding, kind of repurposed for bounding the clique number instead of the independent set number. But as you increase the degree beyond that, you get stronger and stronger relaxations in exchange for kind of paying more and more in runtime. And so you can view these as generalizations of the theta function if you want for the special case of clique. Okay, so what did we want to do? We wanted to see how is sum of squares going to do when applied to the Paley graph, and we think that the Paley graph looks like the Erdős-Rényi random graph. So fortunately, people have studied already sum of squares relaxations of the clique number for Erdős-Rényi random graphs, just as a kind of studying the average case hardness of calculating or bounding the clique number. And what they found is basically a similar kind of square root barrier to what we saw for the Paley graph, right? So they found that on the one hand, the true clique number of an Erdős-Rényi graph is of order log p, right, like we said. But for any finite kind of level, finite degree bound, taking the size of the graph to infinity, the typical value of that SOS relaxation is basically of order square root p. Right? So the same kind of situation that we saw we were in with the Paley graph. And so from the point of view of the SOS literature, there's another kind of related question, which is that this is showing this kind of average case hardness in a very specific sense for a very specific distribution of random graphs, which are these Erdős-Rényi graphs that are kind of maximally convenient to work with. And so it's natural to ask, well, how robust is this? What properties of a graph really does this lower bound depend on? And so from the point of view of sum of squares, there's a related question, which is, can we kind of de-randomize these lower bounds, right? Can we find deterministic graphs that behave roughly at least in the same way as Erdős-Rényi random graphs from the point of the true value of the clique number and the sum of squares relaxations? And there's been a bunch of work on this kind of thing for other problems in sum of squares literature lately. So our results say that the Paley graph works for this only sort of. Right? So we can, first of all, for the first degree, that the Lovász theta function that I wrote down earlier, it's not so hard to show that the value is exactly square root p, using that the Paley graph has kind of lots of symmetries. What we can show is that for the next relaxation, the first kind of non-trivial one, the degree 4 relaxation, the value is of order cube root p. Right? So smaller. but still separated quite a lot from log p or polylog p, which we think is the true value. And so this kind of fits into how the work on random graphs went, where an early result, which was later found to be kind of suboptimal in some technical ways, showed this kind of p to the 1/3 lower bound for this same degree 4 relaxation. So you can ask, okay, kind of what's wrong with our proofs, and can we improve them to square root p? So we did some numerical experiments. I haven't seen any plots like this at this conference yet, so here's a treat for you. So we did some numerical experiments, and we find that actually it seems like the value of this relaxation grows slower than square root p. So maybe the truth actually is somewhere in between these values. Here are some bigger experiments done by other people. These are, so you can just look at the red and green lines, and those are some relaxations which are sort of weaker than, but trying to approximate the degree 4 relaxation. And so all of these things kind of consistently suggest that the true value should be somewhere strictly between 1/2 and 1/3. So you can also ask, can we improve up to whatever this magic number is, which seems to be greater than 1/3 from our lower bound of p to the 1/3. So we, like I said, right, to prove lower bounds, you want to build this feasible point for the dual program, this matrix X satisfying all these symmetries. And we use a kind of simple example that's again inspired by this random graphs literature, where, so remember there's this constraint that on any set indexed by a non-clique, the thing has to be 0, right? This set function. So we say, okay, we're going to make that hold. And then other than that, we're going to choose the kind of simplest possible thing of having this just be a function of the size of the clique. So as part of this long random graph story, Kellner at some point showed that such kind of dual certificates, which is what people were using for a long time, can only prove kind of weaker lower bounds than what they were hoping to see. So in particular, if you plug in d equals 2, which is degree 4 here, you'll see that such things can only prove an order p to the 1/3 lower bound for the degree 4 sum of squares relaxation. And so we can prove, bless you, the same thing for the Paley graph. And so basically, the upshot of this is that we can't improve on our lower bound unless we get out of this particular special class of dual points x, and that will probably be much harder to analyze. This is already, as I'll hopefully mention, quite tricky, and it would be only trickier yet to try to improve. Okay. So now, right, those numerical experiments are giving some kind of surprising indication that actually sum of squares does seem to do well on what seems to be this kind of quite hard, long, open number theory problem. So we asked ourselves, is this really true? Can we find some kind of theoretical, non-numerical evidence for this holding or not? So to do that, you can look way sort of inside of the proofs of these random graph lower bounds. And so ultimately what they depend on is norm bounds on a very large class of random matrices built from your kind of instance, the adjacency matrix, so in this case the plus minus 1 adjacency matrix of the graph that you're trying to prove a lower bound for. So, okay, it's quite complicated and technical, and I don't know. It's just a pain to understand what's going on and all this stuff, but roughly speaking, what happens is it's kind of like a deformed, kind of partially contracted tensor product of this plus minus 1 adjacency matrix A. So what happens is there's some template graph, which is what I drew here. There's one special subset of it that the row labels of your matrix kind of fix labels of. There's one special subset that the column labels fix labels of. And then you sum over all possible ways to assign labels to all the other vertices of the product over the edges of corresponding matrix entries. So if people have seen things like tensor networks, and algorithms built from them, this is sort of quite similar to that. But anyway, this is some huge class of complicated random matrices, and you have to prove norm bounds for them to do this kind of optimal random graph analysis. And what we can show is that there are some cases of this where the norm bound that is correct for random graphs does not hold for the Paley graph. And the Paley graph is kind of much worse behaved. And so for kind of the general analysis, for general degrees of sum of squares, the main technical tool does not kind of de-randomize, but it does de-randomize for small graphs, and so for our kind of modest purposes, things are okay. And so, okay, this I won't talk about very much, but basically the reason for this is some differences in the spectrum, the eigenvalues and the eigenvectors and kind of cancellations that happen among them in the Paley graph as opposed to the Erdős-Rényi graph. It's kind of a subtle point, but roughly we take advantage of some kind of extra structure in the spectrum of the Paley graph to build those examples. So let me say finally a few words about the proof. So like in the random graph case, right, we do have to prove bounds on norms of these big kind of lifts of the adjacency matrix of the Paley graph. But we use a different method. So in the random graph case, they use this kind of classic random matrix technique of taking traces of high powers. So then and taking expectations of those, and then you end up with some combinatorial quantity related to this kind of template matrix H. And then you have to, I don't know, analyze that, and you can relate the norm to some graph properties of that template matrix. For us, there's no expectation to take because the graph isn't random. But we do the same thing, and we end up with what are called character sums in number theory. So there's this function which basically encodes the adjacency relation of our graph, which is just the kind of plus minus 1 indicator of being a square or not over z mod p. Right? This is called the Legendre symbol, and it's a multiplicative character. So the value on the product is the product of the values, and people in number theory, for various reasons, have studied kind of big sums of evaluations of characters, and so we use some kind of tools like that. So there are not very many good tools for our specific situation, but we use the tools that are available, and then we find some tricks to kind of navigate everything that we need for our purposes. So to elaborate just a little bit, this is kind of a very classical fact from analytic number theory, which says that if I take the sum of this character, the Legendre symbol, evaluated on some polynomial, right, over the entire field. So this is a sum of p many numbers, each of which is plus minus 1. Right? The result says that this sum is of order square root p, which is the same order as such a sum would be for random plus minus 1s. Right? So you basically observe the same cancellations as though these were just independent random things. And so this is kind of a manifestation of basically the pseudo-randomness of the graph, because the graph is also determined by the Legendre symbol. So it's the kind of the same phenomenon. What we need is kind of the multivariate case of this. So we need to have multivariate polynomials in many elements of the finite field. And again, we want these kinds of square root cancellations. And this is really a very kind of current topic in analytic number theory. You can handle some cases, not others. It's kind of on an ad hoc basis. It's very fortunate for us that we didn't need to prove new results of this kind, because then we would have to get into this, cohomology of Lease sheaves and whatnot. So we don't know what this means, and fortunately we didn't need to, and we used basically simple tricks plus pre-packaged results from this kind of wild world of modern number theory to do everything that we need to do. Okay, let me wrap up with some open questions. So first of all, right, there's this scaling of this relaxation. We know it's between 1/3 and 1/2, right? So what is this magic number that we see in our experiments? It seems to be kind of better than 1/2, and so that would be kind of exciting from the number theory perspective, but from the complexity perspective, that would leave open the problem of what kinds of deterministic graphs can actually de-randomize this random graph situation sort of fully, and achieve an order 1/2 lower bound for sum of squares relaxations. So from the number theory point of view, it's also interesting to ask, okay, we have these numerical experiments, we have this kind of suspicion that these relaxations prove strong bounds. How can we extract actual proofs of this kind of mathematical claim from these experiments with sum of squares? So we've only talked about the degree 4 relaxation. It would also obviously be interesting to look at what's going on for higher degrees. And finally, so from the really kind of proof complexity point of view, it would be interesting to understand if these sort of propositions, these tautologies about the Paley graph are actually hard, and if so, then for what proof systems can you formulate this and prove lower bounds in other proof systems and so forth. All right, so thanks for your attention. Happy to answer questions.
Studied, at least numerically, the higher degree SOS relaxations?
No. So they are very difficult to run. Even the degree 4 simulations, I mean, you saw on that slide of really calculating the relaxation itself, we can only get up to, like, P is, like, I forget, 200, some hundreds, which does not really give kind of convincing, numerical results to kind of resolve what these asymptotics should be. There's this set of ideas about basically building weaker relaxations that try to approximate SOS, which was that second plot of many more primes that I showed, but we haven't tried to do that for a higher degree, but it's possible. It's just lots of, coding and figuring out how to make the big cluster do run our STPs and stuff. Yeah.
More questions? So for this deterministic question, if you take something like a two-source extractor and pretend it's a graph, a JCC matrix of a graph, would that be a candidate for a deterministic graph that behaves like random?
Maybe, right. So, I mean, there are lots of, candidates around like that. The issue here is that, so the Paley graph does behave like a random graph in lots of ways, but not in the sense of its spectrum. So the Paley graph is a strongly regular graph, and so it has just two different eigenvalues, right? And this is very different from an inter-Shreni graph, which has this kind of semicircle law of its eigenvalues from, so it behaves like kind of random matrices from random matrix theory. And so that's really the kind of criterion of pseudo-randomness that we think is in charge of whether this kind of plan will work. And so really, I think the thing that we want is these sort of spectrally pseudo-random graphs in some sense. And I think this is not something that's been studied very much.
Or if you take like other real characters, like Hadamard matrix, whatever.
Yeah, right. So this is, so that kind of thing would make sense. I think those all have this sort of structure in the spectrum because basically, like if you imagine, squaring the matrix or something, you end up with reductions because of kind of exact character orthogonality or something. But so I can give you the kind of idea that I have of something I think that should work, which is basically like small induced subgraphs in the Paley graph. So if I take the Paley graph and then I look at, let's say, the mutual, I pick a bunch of special vertices and I look at their mutual neighbors and the induced subgraph on there. That operation kind of destroys this structure that somehow is getting in the way. So this is our kind of belief that looks like it's getting in the way of proving these lower bounds. And so that's the best idea that we have for what might work, but it's hard to work with those graphs, exactly because they have so much less structure. So there's some tension.
Great. If there are no more questions, let's thank Tim again and lunchtime.